All right, so this lesson is actually based on a lab. Typically, what we would do is we would have like a tennis ball, maybe a field hockey ball, basketball, things like that. And we would actually perform this experiment. And you're welcome to try this at home. Probably helpful if you have a meter stick or a yardstick in order to just see some of the real data. Many games depend on how a ball bounces. For example, if different basketballs rebounded differently, one basketball would bounce differently off of a backboard than another would. And this could cause basketball players to miss their shots. For this reason, manufacturers have to make balls' bounciness conform to specific standards. In this lesson, you will investigate the relationship between the height from which you drop a ball and the height to which it rebounds. So we've got bounciness statistics. Like, this is a real thing. Tennis balls must rebound approximately 111 centimeters when dropped from 200 centimeters. Soccer balls must rebound approximately 120 centimeters when dropped from 200 centimeters onto a steel plate. Basketballs must rebound approximately 53.5 inches when dropped from 72 inches on a wooden floor. And squash balls must rebound approximately 29.5 inches when dropped from 100 inches onto a steel plate at 70 degrees Fahrenheit. The one you're probably the most familiar with, though, is the basketball. If you've ever seen at the beginning of a basketball game, the official will often hold the ball up and just let it go. And what they're doing is checking for bounciness. They're checking to see whether the ball bounces back as much as they would predict to see if it has the right air pressure. So how can we figure out a ball's bounciness? What we would do is we would take the rebound height and divide it by the starting height. And the reason for that is a ball always bounces back less than where it started. You can also think about this from a science point of view. If you've ever been at a swing set and you pull somebody back on the swing and let them go, they never come back far enough to hit you if they don't pump their legs. They will always come back less than where they started from. And this is sort of the same thing. If you just let the ball go, it should bounce back less than where it started from. Again, that has to do with transfer of energy. Lots of science going on in this lesson. So if we want to figure out which one's the bounciest, we would do rebound height divided by starting height. So the tennis ball comes up at approximately 0.555. Soccer ball should come up approximately 0.6. Basketball should come up at approximately 0.743. And squash balls approximately 0.295. Now, the reason I'm saying approximately is they're not actually testing these scientifically once they get out onto the court, but they do sort of have an understanding. If you've watched tennis before, you'll notice the person bounces the tennis ball. They're also sort of checking for bounciness. So which one is the bounciest? We would say that that would be the basketball because it's the closest to 1. If you let go of a ball and it came back exactly where you started, it would have a rebound height divided by starting height of 1. So the bounciest one is going to be the basketball because it comes back closest to 1. The bouncing ball. How can you determine if a ball meets expected standards? With your team, we will calculate the rebound for a ball, provide you with the items used. If you're going to perform this at home, you are going to want to make sure you use the same ball the whole time under the same conditions. So you wouldn't want to do it one time in a room that's 65 degrees and then another time do it in a room that's 90 degrees. You wouldn't want to do it once on a wooden floor and then the second time on grass, things like that. So what do we need to measure? We would need bounce height, and we would need drop height, also known as starting height. How would we organize our data? We could organize it in a table, or we could organize it in a graph. How can we be confident that our data is accurate? So a couple things that we can do. We can make sure that we test it at different heights, right? We don't want to just test it at one height. And we would want to make sure that we repeat the experiment multiple times. We wouldn't want to just do it once and be like, okay, I'm done. I got my one answer. You might have an outlier. You'd want to perform it a few times. So work with your team to model the data that you collected. So on the back side of your notes, what you're going to see is a place to collect your data. So let's say I have a ball that has a start height of 100 and I perform the experiment 3 times. I got a 70 for a rebound, a 68 for a rebound, and a 69 for a rebound. So the average rebound height would be 69 centimeters. And then I would say my rebound is approximately 0.69 because I did rebound height divided by starting height. And then if I have 90, with an average here, 62, 63, 64, an average of 63 centimeters. That's approximately 0.70. And that's rebound height dividing by started height. And then 45, 44, 43, that's an average of 44 centimeters. I'm getting approximately 0.73. 39, 39, 39, that's nice and consistent with an average of 39. And rebound height divided by start height would be 0.78. And then the last one, 24 centimeters is my average if they're all 24, with approximately 0.80. Now, I hope you notice something here. This is changing, right? When we drop it lower, we get a higher rebound ratio. When we drop it from higher, we start getting a much lower rebound ratio. Now, this should tell us something. This should tell us that it's probably not linear because the rebound ratio is changing. If every single time we got 0.7, 0.7, 0.7, 0.7, 0.7, we would go, oh, look, that's linear. We're getting a constant rebound ratio. For now, we're going to explore based on what we knew previously. If I average those 5, add them up and divide by 5, I get an average of about 0.74. And I can also graph that. Now, in order to graph that, we want to talk about what goes where. So if we look back at the front of our notes, it says, does the height from which the ball is dropped depend on the rebound height, or is it the other way around? Which one is your independent variable and which one is your dependent variable? So your independent variable is the one that you have control over, and that's going to be your start height or your drop height. And the dependent variable, the one that depends on the other, is the rebound or the bounce height. Because how high it bounces depends on how high it started. When the points on a graph are connected, it makes sense to connect them. The graph is said to be continuous, but only if it makes sense to connect them. Okay? So for something down here like gas in gallons is something that we measure. And so that one is connected because we can have 1.2 gallons, we can have 2.5 gallons, and so on. But if we're buying shirts, we can buy 1 shirt or 2 shirts or 3 shirts, but we're not buying 1.5 shirts. So this one would be discrete data, for example. And so we would not connect the dots on this one because it doesn't make sense to use 1.5 in the middle. So should our rebound height graph be discrete, where we've got whole numbers, things that we are counting, or should it be continuous, where it's something that we're measuring? And very clearly, the fact that we would have to have a meter stick or a yardstick tells us that we're measuring. It should be continuous. I-N-U-O-U-S. Wow, spelling. Because it is measured. All right, so it is continuous. So the example that we're doing, we are going to draw a line. And in this case, it's going to have to be a fitted line because our data does not line up perfectly. So we can talk a little bit about stuff from chapter 4. If we look at our data and we say, okay, if we had a start height of 100, so we'd go over to 100 and we bounced back to 69 centimeters, we would go up here to just shy of 70 and put a dot. And then we had 90 and our average was 63. I'll be right about here. And then we had 60 with a bounce back of 44. Right here, just below 45. And then if I go over to 50, I had a bounce back of about 39. And 30 had a bounce back of about 24. So those dots actually look pretty linear. I mean, we've got a very small set of data, only 5 points. And actually, those numbers are quite low. So if we wanted to graph them, you know, that's pretty linear, right? From a quick glance. It says, graph your results from problems 519 on the grid provided below. Draw a line that best fits your data. Should this line go through the origin? Okay, so that's a good question. Should it go through the origin? 0, 0. If I have a start height of 0, what's the rebound height going to be? Well, 0. So we would say, yes, it should go through the origin because it should go through 0, 0. So 0, 0 is a reasonable point because a drop height of 0 results in a bounce of 0. All right. Write the equation of a line that models your data. Well, we found that our average ratio was 0.74. So it seems that that would be like the equivalent of our slope. We're saying that when we divided the rise over the run, we were getting approximately 0.74. So we would go with y equals 0.74x. There'd be no plus or minus because we are assuming that this should go through 0, 0. That seems reasonable. Y on the y-axis was our rebound height. And x-axis, we had our start height. And what is the mean rebound height for all of them? We said it was 0.74. That was the average. Where is it reflected in the equation of your line of best fit? It would be our slope. It would be our rise over our run. So if I want to go up here and I want to put in a fitted line of 0.74, I am going to specifically aim for going through 0, 0. And if we want to have 0.74, we'd go over to 100 and we'd go up to 74, which would be about there. And we would sort of aim for those 2 points because that would give us a slope of 74 and it would go through the origin and we would end up with something about like that. Now, could you use your graphing calculator? Absolutely. So if you wanted to use your graphing calculator to do this, you would use your start height as X or L1. You would use your mean rebound height as Y or L2. And then you could ask it to do a fitted line. And it would do approximately what we just did manually on the graphing calculator. And you're welcome to play around with that. It's only 5 points of data, so it wouldn't take you very long. All right, so we're going to continue to move on from here. But for right now, because of the set of data we have, it kind of looks like it's linear. We've got a couple points above. This one pretty much looks like it's on. These look like they're below. So it looks pretty evenly spread. I don't have any reason from the graph to think that it's anything but linear. However, when we look up here, this changing pattern for the rebound ratio does start to get a little bit suspicious. See you in class.